this is like, this section of this class is a lot, I think. There's a lot of stuff happening and a lot of calculations. I'm going to give you ideas and then we're going to compute a bunch of examples of it. Some of this is going to involve working with complex numbers. If you have a calculator and you'd like to know how to work with complex numbers, just let me know and I will show you how you can use I, like the imaginary unit on your complex, or your calculator, because it will happily do it for you. The other thing that I discovered is that I went into the office to check what I was teaching in the fall, and I am teaching 344. So any of you guys that want to go on in 344 in the fall, I have 2 sections of it. So right in the middle of the day, 12 and 1. Okay. The other students asked me if I would please have an honors section of it, and I'm not sure that I can actually that I have the pull to do that because it's probably not enough of you. But I mean, you get in early. Apparently my classes fill up, so anyway, okay, so what we're doing today is we are going to talk about the eigenvector and eigenvalue problem, hopefully with more of an eye towards what's actually happening. And then I'm not going to be able to do it today, but I'm going to start pointing to why we're doing this, like what the structural implications are. So we're talking about 7.1, which is sort of eigen stuff. So eigenvalues and eigenvectors. And the first thing that I want to remind you of here is the notion of a linear function. So every square matrix A, say n by n, induces a linear function f that takes Rn to Rn by eat the vector and multiply it by the matrix. So every matrix you can make into a function. Then the same sort of functions that we dealt with when we were like back in 241. So you eat a vector, the function is take the vector, multiply it by the matrix, the thing that comes out is the same size. This is linear, of course, because if I took f of ax plus by, I take a linear combination of vectors of the right size. Matrix multiplication satisfies all the rules of algebra. I can take this and I could distribute this to get a times ax plus b times ay, because scalar multiplication does actually commute with matrix multiplication. And this is just a times f of x plus b times f of y. So a matrix multiplication induces a linear function. There's a theorem I don't really have time to go into a lot of detail on, but actually the reverse version of this idea is more interesting, which is it turns out that if f takes, say, Rm into Rn is linear, so any linear function, so differentiation or integration on a finite dimensional vector space, if f is a linear function, there exists a matrix A so that f of x is equal to a times x. This is called the matrix that represents the function f. This is an enormously important idea that I have nowhere near enough time to actually teach you. So if you want to learn about that theorem, I can point you to where it comes out in your book. I think it's in chapter 5. I spent sections of chapter 5 talking about this idea. So this is part of the reason why this matrix mathematics is so useful, is that you can represent really complex set of functions with matrix multiplications. Okay, so if we knew that we had a matrix that we had turned into a function in this way, it turns out that there are sort of special vectors. Every square matrix A has associated special vectors V, so that f of V, that is if I apply the function of multiplying by the matrix A, I get the same vector back out again, but scaled by some scalar lambda. That is, what f is doing is a function, is a linear transformation. What f is doing is it's eating a vector and spitting out a vector that points in the same direction. This is the sense that was originally used to come up with the idea of eigenvectors. Any vector that satisfies this property where f of v, which is av, is equal to lambda v, that is what we mean by an eigenvector, and lambda is its associated eigenvalue. Okay, so these such of v is called an eigenvector, and lambda is called the associated eigenvalue. And the reason that we don't just want to trap ourselves into talking about matrices is later on it's going to be important to consider the case where f is a linear function, but maybe we don't know what its matrix is. So, for example, when I wrote down, say, f of a function g of x is equal to d by dx of g of x. So f is the function that differentiates. That's a linear function. So when I write down f of e to the 2x is equal to 2e to the 2x, this also satisfies the definition of being an eigenvector. F of the thing gets the same thing but scaled by a number. So I can think about eigenvectors as not just being attached to matrices, but to any linear function like this. If f is the function that eats g and takes a derivative of it, it's certainly the case that f of e to the 2x is 2e to the 2x. And this satisfies the that condition. Okay. So ultimately, depending on what your flavor of engineering or applied mathematics is, the idea of functions as eigenvectors turns out to be really important. Okay, so next we are going to talk about how you find these things. So last time, I sort of ripped through an algorithm that we could use to at least verify that things were eigenvalues. So how do you find them? How to find eigenthings. This is the way everybody talks about this stuff. You put eigen on front of anything. How do you find some eigenthings? Not a formal definition necessarily. So we're going to start by, let's assume that we're given a matrix A, a scalar lambda, and a vector v that satisfy A times v is equal to lambda v. This equation right here is called the eigenvector equation. And what I want to do is I'd like to know all the vectors, if I can, all the vectors that satisfy it, which is called the eigenvector problem. But so we're going to go looking for a condition that we could check that would tell us that we had a solution to this equation. So we're going to work backwards. Let's assume that we had a solution. So if I have a solution to this equation, there's one assumption we have to make here that I need to add. V is not the zero vector. So V has to be non-zero. So the formal definition of an eigenvector is non-zero. So if I knew this, I could use algebra to rearrange this equation. And that would get me AV minus lambda V is equal to the zero vector. Ultimately, I want to use, so this is a class where the only tool we've got is row reduction. I want to turn this into a row reduction problem. I got my hammer. I'm going to turn this problem into a nail. Yo.
Why are they not just this, like, what, is it because it's matrices we're dealing with? Why are they not just the same number?
A is not a number, it's a matrix.
So you're making a matrix?
I'm starting with a matrix A, which could be n by n, and I've got a single number lambda where I can hit it with a vector v, where multiplying by the matrix is the same as multiplying that vector by a number. right? So to make this more concrete, this is an example that we'll look at later. If I looked at the matrix, so one thing that we'll show is that if A was equal to 3 minus 1 minus 5 minus 1, and you took that matrix A and you multiply it by the vector, I think 1, negative 1, is that right? Hold on a second here. Yeah. So so ultimately what we can show is that if I took this matrix, 3 minus 1 minus 5 minus 1, and I multiplied it by the vector 1/5 1, when you do that, what you get out is negative 2 times the vector 1/5 1. So if you actually concretely calculate this matrix multiplication, what you're saying is you could go through the computationally expensive process of multiplying this vector by this matrix, but if you knew it was an eigenvector, you could just multiply it by its eigenvalue, right? So it's a computation-saving thing to know that. Somehow, structurally, for certain vectors, this matrix is the same as scalar multiplication. So what we're doing is we're going to start by trying to figure out where these come from, how we can extract this information from a matrix. So we're going to start by assuming that we have a setup where this works. I'm going to try to work backwards for something that we can say about the matrix where we can use row reduction somehow. So I look at that algebraic rearrangement of the equation and I think, it sure would be nice if I could factor the v from both sides of that equation, but I can't because that's a matrix and that's a scalar, and what would be left behind would be a minus lambda, which makes no sense. You can't take a matrix minus a number. So what I'm going to do is I'm going to cheat. And I'm going to observe that I could have multiplied by the identity matrix, and the identity matrix times a vector doesn't change it. Right? That's like multiplying by the number 1. And now I've made something I can factor the v's off of, because now I've got a matrix times a vector minus another matrix times a vector. So I could factor this as a minus lambda times the identity times v is equal to 0. Now v is not the 0 vector. V is not 0. So if v is not the 0 vector, what do I know about the null space? What do I know about the null space of a minus lambda I? How many vectors are in the null space of lambda I? Remember, the null space is just the set of solutions to the equation matrix times vector is equal to 0. How many vectors are there in there? Okay, well, there's definitely 2, but I can say more than that. When you're dealing with a matrix problem, there's only 3 possibilities. The system is inconsistent, in which case there's no solution, or it's consistent. And what are the 2 possibilities when a matrix equation is consistent? Either one answer or infinite answers, right? I already know the 0 vector solves this equation. That's a one answer that will always solve this equation. So as soon as I know there's another answer, how many things are inside this null space? There's an infinite number of them, right? There has to be infinite. This is like the worst kind of counting, either 1 or infinite. Okay, if the null space of that matrix is infinite, there's an infinite number of solutions, what do you know about the row reduced form of this matrix?
The last row is all 0. The last row is 1 row.
What are you going to say?
That.
Is it the last row? Some number of rows?
Any?
What's that? Okay, so yeah, so the row zeros and linear dependence are all the same thing, right? So that basically, yes, there has to be, what I'm looking for is something to do with the columns, right? If you did the row reduction and you were looking down the columns, how do you know that you got linear dependence in the columns of a matrix? What shows up in the row reduced form?
There's 3 variables.
Free variables, right? Infinite solutions must correspond to free variables. Oh, well, if the null space of this has infinite, is infinite and not just a single vector, then the row reduced form of a minus lambda I must have a free variable. At least one. At least one free variable. What's the determinant of a matrix with a free variable? 0. It has to be. There can only be a free variable if there's not every column is a pivot column. And the only way you can have columns that aren't pivot columns is if there's a row that has nothing in it. So, basically from here, the row-reduced form of that matrix must have at least one free variable, which means it must have a row of zeros, at least a row of zeros, and that means the determinant of A minus lambda I has to be 0. If the determinant of a matrix is 0, the determinant of any row equivalent matrix is 0. It has to be. Because there's only 3 things you can change with row operations with a determinant. You can keep it the same if you do the linear combination. You can multiply by -1 if you row swap. Or you can multiply it by a non-zero k if you scale. Every one of those, if any of the matrices is 0, all of the rest of them that are row equivalent also have 0 determinant. These are the non-invertible matrices. So look at what that says. That says if we had started with a solution to this, if we had an eigenvector, the determinant of this matrix must have been 0. This is the condition that tells us that it's even possible to have an eigenvector. So what we're going to do is we're just going to reverse this. We're going to look for places, numbers that make this determinant equal to 0. And what that will do is it will tell us that this equation has non-trivial solutions. Something is in this null space besides the 0 vector. And that's what our algorithm is going to look for. So let me reiterate that. So in the other direction, we would say the following. If the determinant of A minus lambda I is equal to 0, then A minus lambda I times V is equal to 0 has non-zero solutions. It has to. If the determinant was not 0, that would have unique solution. It would be the 0 vector. But because the determinant is 0, there are free variables, so that has non-zero solutions.
Wait, V has non-zero solutions?
No, the equation. This is, you think of this as the variable. So I'm reversing it now, right? So now I'm just writing the equation down. Hey, if I could figure out a lambda that made this true, then this equation must have vectors v that solve it that are not the 0 vector. If they were only the 0 vector, that determinant would have been something other than 0. But if this has non-zero solutions, any such non-zero v that solves it, any non-zero v with A minus lambda I times V is equal to 0 can be rearranged to say that AV is equal to lambda V. If that determinant was 0, then I can find vectors that solve this equation. So this is the condition that we're going to check to find eigenvectors. Solving this equation will tell us the eigenvalues. Solving this equation will tell us the eigenvectors. So that's what the algorithm is going to be. And then we're just going to do a ton of examples of doing it. So how do you do it? 1, so you're given some matrix A. Step 1, you are going to solve the equation, the determinant of A minus lambda I is equal to 0 for all the values of lambda that do it. This will be a polynomial. So there's only going to be a finite number of solutions. You can list them. Lambda 1, lambda 2, lambda 3, out to lambda k. There could be one of them, there could be 2 answers, there could be 3, all the way up to n, where n is the size of the matrix. Having found them, for each eigenvalue, what's that?
What's the difference between A and N?
Oh, because I could just have, for example, I'm going to write down matrices where it's a 2 by 2 matrix but with only one eigenvalue. right? K is some number that could be as large as n, but doesn't have to be.
Okay.
So an n by n matrix could have 1, 2, 3, 4, 5, 6, 7, blah, 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 and n minus 1, or n distinct eigenvalues. So I'm just accounting for the fact that the length of this list may not be n.
Okay.
So these are, distinct. So for each eigenvalue lambda I, we're going to find the null space of the matrix A minus lambda I times the identity matrix. Once I know that I've got the right lambda, finding a description of this null space will tell me what all the eigenvectors for that eigenvalue must look like. So I start by finding the eigenvalues, and then I go one by one through the eigenvalues, and I calculate null spaces. A lot of row reduction involved in this. So you're hoping for 2 by 2 or 3 by 3 matrices, or I give you row reduced matrices on an exam, and I will show you how to use your calculators for this if you haven't done it before. So this is actually easier to demonstrate, I think, by example. So the matrix that I wrote down earlier was A, so this is example 1. And I think I wrote down the matrix, was it 3 minus 1 minus 5 minus 1? Was that the?
Yeah.
I think I had that written down. 3 minus 1 minus 5 minus 1. Okay, step 1 says I would like to find the eigenvalues of that matrix. So step 1, find the eigenvalues. How am I going to do it? I'm going to solve the determinant of A minus lambda I is equal to 0. This is an algebra problem. So in order to do that, I should probably write down what A minus lambda I is. So A minus lambda I, lambda is our variable, is equal to 3 minus 1 minus 5 minus 1 minus lambda times the identity, which means there's lambdas times the identity. If you subtract, you get 3 minus lambda minus 1 minus 5 minus 1 minus lambda. The algorithm says to take that and calculate its determinant. So we're trying to solve this equation. Well, 2 by 2 determinants are easy at least. You hope all the examples I give you to do yourselves on an exam are 2 by 2. So the determinant of A minus lambda I is the determinant of 3 minus lambda minus 1 minus 5 minus 1 minus lambda. And that's equal to 3 minus lambda minus 1 minus lambda minus negative 5 times negative 1. I think when you're done foiling this, you guys can verify for me here. You get a lambda squared, and then a lambda and a negative 3 lambda, which is minus 2 lambda. And then there's a negative 3 and a negative 5, which makes a negative 8.
Yeah.
And this thing is called the characteristic polynomial. You can think about it as revealing lots of structural information about the matrix. If we solve for the roots of that, so now we're going to solve lambda squared minus 2 lambda minus 8 is equal to 0. So lambda minus 4 times lambda plus 2 is equal to 0. So lambda is 4, or lambda is negative 2. Right there, those are your eigenvalues. Successfully completed step 1. Wait for the enormous helicopter division. I mean, it was like the fire alarms went off back in whenever that was, where you canceled. With you guys, I canceled class last term? I don't think so. All right. So step 2. Step 2 says. That tells me the eigenvalues, but it doesn't tell me the eigenvectors. So if I want to extract the eigenvectors that go along with those, I'm going to go through them one at a time. So I'm going to start with lambda is equal to 4, and I'm going to find the null space of A minus 4I. Once I have the eigenvector, the specific, or the eigenvalue, the specific eigenvalue, I can plug it back in to the matrix and then do a null space. So for this one, you get A minus 4I is the matrix. 3 minus 4 is, I think I got this right. 3 minus 4, let me do that. Let's make sure I've got this correct here. 3 minus 1 minus 5, there's a 4 here. So 3 minus 4 is negative 1, and then minus 1, and there's a minus 5, and then 1 minus 4 is minus 5. The fact that that thing has an obvious dependence between the columns is good. We want there to be a dependence between the columns, because otherwise there's no eigenvector. The eigenvectors are in the null space of that matrix. So to calculate the null space of the matrix, what am I to do? Row reduce. I augment with zeros first, and then row reduce. We got one tool, it's row reduction. That's all we got. So to calculate the null space of minus 1, minus 1, minus 5, minus 5, we write down minus 1, minus 1, 0. We augment with the 0 vector. We row reduce, which gets us 1, 1, 0, 0, 0, 0. And now we do the same procedure that we've done a bunch of times already. We're going to parametrically write down the solution set. There's a free variable here. If you do one of these and you don't get a free variable, you're wrong, right? Because that means the only answer is the 0 vector, and the 0 vector can't be an eigenvector. These numbers were designed to force this thing to row reduce to something with a row of zeros. All right, so what does that mean? How do you interpret this? You would say C2 is free, and C1 plus C2 is equal to 0, which means C1 is minus C2. And so the solution set here looks like C1, C2 is equal to minus C2, C2, which is C2 times the vector minus 1, 1. And that thing right there, that's your eigenvector. So a lot of times when we're doing these problems, if I want to save this information, that eigenvector goes with this eigenvalue. They come together. And so there's another bit of mathematical lore here. These together are called an eigenpair. This is actually a term that gets used. So one of the eigenpairs for the matrix is the eigenvalue 4 and the corresponding eigenvector minus 1, 1. That specific combination tells you that if you took the original matrix and you multiplied it by minus 1, 1, you should get out 4 times minus 1, 1. We can verify that really quickly by just writing down 3, minus 1, minus 1, minus 5, and multiply it by minus 1, 1, and you get negative 3 minus 1 is negative 4, and 1 minus 5 is negative, I think it's right, positive 4. No, negative.
To the row, not the column.
1 minus 5 is minus, what the hell?
I think you flip the bottom row of the matrix.
Did I flip the bottom? Oh, is it supposed to be 5?
Yeah.
Sorry, my bad. Minus 5, minus 1, there we go. That fixes it. 5 minus 1, which is also 4, which is whatever.
Top one is negative.
Negative 4. What's
You got negative 4 originally correctly.
All right, I fixed it?
Yeah.
Okay, which is 4 times the original vector. Okay. So at least you should believe for this one specific, I mean, obviously if it works once, it must just be true, right? So since I did it one time and I showed you this one correct vector, it must work for all vectors.
Yes.
Anyways, the idea is that what we got out here is this relationship that we've written down is exactly the fact that this pair solves this equation. A times V equals lambda times V.
And is that vector going to be the same for any value of lambda?
No.
So it's a different vector if you put in
It is a different vector if you put in the other number. So if we do the same, so we're just going to do a bunch of these calculations basically. So we're going to do the same exact process, but now we're going to do it for the other eigenvalue. So I'm going to do step 2 again. Now I'm going to let lambda equal -2. And if I do that, I get a minus -2i is equal to the matrix. Okay, so it was -3 plus a 5, -1, -5, 1 is what comes out when you do that. Again, obvious linear dependence. It won't always be. If you calculate the null space of that matrix, so if you write 5 minus 1 minus 5, 1, 0, 0, and you row reduce it, you get 1 minus a fifth, 0, 0, 0, 0. So again, you have a free variable, which is what we're looking for. And so the solution set for that null space is going to turn out to be C1, C2 is equal to 1/5 of C2 times C2, which is C2 times the vector 1/5, 1. You can just read off here. C2 is free, and C1 minus 1/5 of C2 is equal to 0. So this is your second eigenvector. That is the eigenvector that goes with lambda is equal to -2. One of the things that must be true is that every eigenvalue has to have at least one eigenvector. It has to. Okay. So the other eigenpair for this matrix would be, or one other eigenpair would be -2, 1/5, 1. And I want to observe here, any multiple of 1/5, 1 is also an eigenvector for the matrix. I can scale this any way I want. Remember, what an eigenvector geometrically says is, if I take that vector and I multiply it by this matrix, it comes out pointing the same way. So if I took that matrix and I multiplied it by 5, it's still pointing the same direction. So it also will have its direction preserved. Every scalar multiple of an eigenvector is also an eigenvector.
So you only need the eigenvalues to find the eigenvector?
Yeah.
What if you have because it's a square number, like lambda minus 1 squared?
I'm going to show you an example of that right now.
Got it.
Okay, so let's look at 2 different cases of when that happens. Okay, so here's a really easy one. This is a funny one. I'm going to write down the matrix 1, 0, 0, 1, and I want to find its eigenvalues and its eigenvectors. This is example 2. Find the eigenvalues, find all the eigen stuff. Okay, so the determinant of A minus lambda I is equal to the determinant of 1 minus lambda, 0, 0, 1 minus lambda, which is equal to 1 minus lambda squared. So it's possible for eigenvalues to repeat themselves. This is 2 repetitions. So 1 minus lambda squared is equal to 0 if lambda is equal to 1 with multiplicity 2. So this is something I'm going to show you guys next time, the idea of multiplicity. The number of times that that term shows up in this factored polynomial means something. So I'm just introducing the idea before I've actually formally defined it for you. So it's got one eigenvalue. If I want to find the associated eigenvectors for this, this is a sort of amusingly terrible calculation here, because it's really easy and stupid, is, okay, what does step 2 say I'm supposed to do? I'm supposed to actually calculate the null space of A minus 1I, which is 1001 minus 1001, which is 0000. So I'm going to calculate the null space of the 0 matrix. So the null space of 0, 0, 0, 0. Okay, I know this is pretty complicated. What I'm going to do is I'm going to augment that with a column of zeros. I'm going to row reduce it. 0, 0, 0, 0, 0, 0, augmented column. Where are the free variables? Yeah, there's no pivots. x1 is free. And also x2 is free, or sorry, c1 and c2, whatever your favorite letters are. And so that means the solution set to this looks like c1, c2 is c1 times 1, 0 plus c2 times 0, 1. There's a two-dimensional set of vectors that corresponds to that eigenvalue. That's only possible because it repeats, because there's more than one copy of it. These are both linearly independent eigenvectors for the same eigenvalue.
Where do you have the one from? Are you just saying no because we have to?
Oh, it's because there's no free variable here, so there's no relationship between c1 and c2 since they're both free. So you write this as c1, 0 plus 0 c2, which is c1 times 1, 0 plus c2 times 0, 1. So it's a dumb parametric solution, right? So generally what could happen is you could have a matrix where there could be more than one eigenvector associated with an eigenvalue. Linearly independent eigenvectors. So that's one possibility. I mean, this is a really stupid example because it was the identity matrix. Now let me show you a worse one. So generally what happens here is the number of vectors that will be associated with an eigenvalue has to do with the power that shows up in the factored form of the characteristic polynomial. But it doesn't have to be all of them. So let me see if I can show you what I mean by that. Let's do exactly the same calculation, but instead, I'm going to do it, I'm going to erase everything because I know otherwise people will try to write over their own notes. So this is exactly the same, except up here, I'm going to put the number 1. That's a 2 by 2 matrix. It has the same characteristic polynomial. Find the eigenstuff. The determinant of A minus lambda I is the same as the determinant of 1 minus lambda, 1, 0, 1 minus lambda. That determinant is also 1 minus lambda squared, because you've got 0 times 1 over there on the other side. So this also has the eigenvalue lambda is equal to 1. I could say multiplicity 2 if I want to. I'm not. We haven't formally defined that yet, but it would be. What do you mean plus 1? Well, 0 times 1 is 0, right? So it's not there. So the point is it has the same characteristic polynomial. Those are different matrices, but this polynomial was the same. So these have the same eigenvalues. This matrix and the other have the same eigenvalue. The difference is if you come through and you solve the null space of that matrix again, so what are you supposed to do to find the eigenvectors? So step 2 is the eigenvector step. You're going to find the null space of A minus 1I, which is, okay, A was 1, 1, 0, 1, minus 1 identity matrix looks like this. So the matrix now we're finding null space of is 0, 1, 0, 0. And that matrix, if I found its null space, 0, 1, 0, 0, 0, 0. Oh, it came pre-row reduced for me. That's nice. So where's the free variable here? C1 or C2? C1 is free. And what's C2 equal to? 0. C2 is 0. So the solution set to this looks like C1, 0, which is C1 times the vector 1, 0. So this is a matrix that only has one eigenvector. There's one eigenvector. I mean, one direction that corresponds to eigenvectors. So I can, at most, I can write down one linearly independent eigenvector. Matrices that do this are so bad and so hard to work around that mathematicians have given them the name defective. They're so broken that they're like, oh, there's not enough eigenvectors, so we don't want to deal with those, right? So defective. Okay. The idea here is there's no way to predict by looking at the structure of a matrix if it will what its eigenvalues will be, and if you know the eigenvalues, just because this has a square term on the 1 minus lambda. In one example, we had 2 linearly independent eigenvectors. In this one, we've just got 1. All right, last case I want to talk about today. All right, questions about any of this so far, other than y, which I promise I'll show you in the future.
If you multiply 1, 0 by your original matrix,
You get 1, 0 out again.
oh, you get 1, 0. Okay.
Yeah, so if you took 1, 1, 0, 1, and you multiplied it by anything parallel to 1, 0. So let's suppose you put pi 0 in here. That's parallel to 1, 0, right? Then what do you get? You get pi plus 0 and 0 plus 0.
And that's pi times 1 over whatever.
Yep.
Like for the determinant part of it, like is that like the only purpose of the determinant is to find that there is a free variable in it?
It's to find the values that force the free variable. Basically what you're doing is you're hunting for the directions that make that matrix fail to be invertible, which means that you know there's some direction. It's like basically an algebraic way of uncovering the directions that don't change, the directions that don't change when you multiply them by the matrix.
Like, what does that have to do with the invertible part? Like, I get that there's like it prove it is.
Oh, because if the determinant of a matrix is 0, and there has to be a row of zeros inside of it, what do you know about every invertible matrix? What does it have to row reduce to? Do you remember?
It's 0, but I didn't.
No. Do you remember what it has to row reduce to? Every invertible matrix row reduces to what? The identity, because there has to be a pivot in every column, right? So that determinant is always non-zero because you multiply down the diagonal and you get 1, right? So if you row reduce to the identity, you could not have had determinant 0. Your columns were linearly independent. Every problem has a unique solution. There's this thing called the invertible matrix theorem that tells you that these things are all equivalent to each other. So if the determinant is 0, then there's a row of zeros in the reduced echelon form of the matrix, and the determinant is also 0. If it is invertible, it row reduces to the identity, and the determinant must have been 1 times the charge that you paid for the row reductions that you did.
Okay.
Yep.
The previous problem, we had 2 eigenvectors. Both of those worked to get
Yes.
themselves out? Okay.
They do.
Got it.
Right, and so that's together, we're going to do this next time. That's called the span of those is called an eigenspace. Because everything has to have eigen in front of it. I know. And then when you put it all together, you build something called an eigendecomposition. So it's all right. Now the last one, I spent a whole bunch of time yesterday railing about complex numbers. So let's write down a matrix where the book has carefully done this one. This is an example of a matrix that looks like this. So A is equal to the matrix 9, 37, minus 1, minus 3. Before we start, I want you to observe that has all real entries.
Okay.
Right? It does. All the entries of that are real.
We're going to get a complex number.
So if you calculate the determinant of A minus lambda I, then you get the determinant of the matrix 9 minus lambda, 37 minus 1 minus 3 minus lambda. And if you calculate that, when you're done, what comes out of this is lambda squared, minus 6 lambda, plus 10. So I'll spare you the algebra, but that's what comes out at the end. So now, if you put that polynomial into the quadratic equation, because you guys love the quadratic equation, you'll find that the discriminant is negative, which means that you're taking the square root of a negative number, and so this has, like, complex numbers are the answers to this polynomial. It does not, this has no real roots. So, if you're not crazy, and you would complete the square on this to figure out the values lambda, because it's like it comes pre-simplified for you. So if you set lambda squared minus 6 lambda plus 10 is equal to 0, and then slide the 10 over to the other side, and then add the 9 that you need to make this a perfect square, and then factor the perfect square that you just made, and then square root both sides, plus or minus the square root of negative 1, fortunately we know that's equal to I, then you get lambda is equal to 3 plus or minus I. Oh man, complex eigenvalues. Now before I proceed, what the hell does that mean? Complex eigenvalues? Everything we wrote down before, I keep saying, oh, eigenvalues represent you're picking out a direction that doesn't change. An eigenvector points in a direction that doesn't change, and the number you multiply by tells you how to scale a vector. How the hell do you scale a vector by a complex number and have that make any sense? These are matrices that rotate the plane instead of like fixing directions. If I took every possible vector in the plane and I rotated the whole plane by 45 degrees, no vector points in the direction that it started pointing in. If I rotate the plane, nothing can have the direction preserved, right? Not a single vector can be pointing in the same direction because you've taken the whole plane and turned it. So there can be no real eigenvectors. There can't be, because otherwise there would have been directions that were preserved. Complex eigenvalues represent matrices that rotate. So when I keep telling you guys there's no escaping complex numbers, this is exactly what I mean. Things in reality rotate. It's unfortunate, but they do. So, how are you going to find... Oh, damn, we got these complex eigenvalues. How are we going to find their eigenvectors? Exactly the same way. 2. We're going to write down the null space. We're going to find the null space of A minus... Well, I got to pick one of them. So how about A minus 3 plus I times the identity matrix? Which means that we're going to be finding the null space of 9 minus 3 plus I, 37 minus 1 minus 3 plus I. Now your calculators do have the ability to work with the complex numbers, right? There's an I on your calculator that it will happily look at if you want to row reduce a matrix using it. When you do this, if you calculate this null space, you take that and augment it with zeros, and it actually row reduces to the matrix 1, 6 plus I, 0, 0, 0, 0. After all, I promise, you could by hand do this if you want to, because you can multiply by complex numbers, you can divide by them. The same exact rules work here as work for the real numbers. You just have these I's running around all over the place, which is obnoxious. Okay, so without being intimidated, we say, what's the free variable here? C2. C2 is free. And the relationship between C1 and C2 is that C1 is equal to negative 6 plus I C2. And so your solution set, C1, C2, is minus 6 minus I C2, C2, which is C2 times minus 6 minus I 1. And that is a complex eigenvector. The eigenvectors have to be complex because they represent rotations. And if they weren't complex, I could plot them in the plane. Oh, that was the direction, and they ended up pointing the same direction. Okay. So I know this is a lot. Read this stuff. Practice these questions. Next time we'll do some more examples, and I'll start bringing in some more of the structure, and we'll start seeing why we're doing this. You should think about the big picture here is essentially in the same way that we take polynomials and we factor them, this is a way of pulling matrices apart into their basic pieces. That's kind of what we're doing here. Yep.